Hello, welcome to my Tech Fun. My name is Igor and I have another filament comparison or testing video. And I was curious what's so special about PCTG. And I want to compare it with PETG. And to be more comparable, I decided to use filaments from the same manufacturer, and that's Fiberlogy. And I bought these filaments myself, so nobody sent them to me. I mean, from your aspect, it doesn't matter. I just want to show you that I'm spending wisely those donations. And about PETG, so probably you are already familiar with this material. It's PET, which is material used for these bottles, with adding some glycol, so it's more printable. Compared to the PLA, it has a little bit higher temperature resistance. It is very good for some functional parts. For example, plastic parts on my Prusa printers are made from PETG. It is easier for printing compared to the ABS because it doesn't warp and it doesn't need an enclosure. You have to pay attention to the drying, so it may absorb moisture from the air, so from time to time you may need to dry the filament. But it is not so sensitive like nylon. For example, usually I use it out of the box. I print something and immediately after the printing I put it in some vacuum bag with some silica gel inside, and I don't have to dry it. But if you need to dry it, basically any filament dryer on the market can dry this, because for example for here we need 60 degrees Celsius 4 hours for total drying according to the website on Fiberlogy. About PCTG, it is a great alternative to the PETG, and it offers increased impact strength, higher temperature resistance and clarity. Now about its impact strength, according to the website, it has 90 kilojoules per square meters, the impact energy, and compared to the PLA it is 10 times stronger. And if this is true, probably this will be the second filament which will not break on my Izod impact test, where I'm using the half kilogram hammer, so I have to raise it a little bit higher, or maybe I had to switch it to the 1 kilogram hammer. I will see. About printability, we have some information here on the stickers. PETG, it has to be printed between 230 and 250 degrees Celsius according on the website. Here it has from 220 degrees Celsius. The bed temperature has to be heated up to 90 degrees Celsius. About the bed, be careful, because some materials may stick too good to the PETG, so it is recommended to use some kind of additional layers, which will be the separation layer. PCTG, it needs higher printing temperatures between 250 and 270 degrees Celsius, and the bed temperature has to be between 90 and 110 degrees Celsius, and you still don't need printing inside the enclosure. About the fans, yes, I forgot to mention, here it has to be between 0 and 25%, and here between 25 and 50% according to the website. About the price, well, it will vary at depend of your country. Here I can see the prices which I paid here in Hungary, in Europe, but basically the PCTG is approximately 36% expensive material. In my test, PETG is a pure or transparent color, and the PCTG is in graphite color. I will print those standard test specimens, so all results will be comparable with those which I did in previous videos, and the results you can download from the Excel table on my website. Let's start with the printing. Very interesting, unique spool. It has this vacuum packaging, because very important with PETG it must be dry, and I will not dry it, I will use it out of the box before the printing. It has only these two holes for locking end of the filament. It would be good if we have a little bit more, and here we can see how many filaments we have on the spool, but it would be good to have some kind of scale here. And now I notice this bag is resealable, so cut it here above this sealing line, and after the using you can place it back, put some silica gel inside and close it. And there are some additional instructions on this paper. Since PETG don't need printing inside the enclosure, I remove it and it will be printed on open printer. And I will print on Prusa's textured PEI sheet. because in this case I don't need any adhesive separation layer for the printing of PETG. Printing is finished, and immediately I always check the adhesion, which is okay, great actually. And I have to wait until this texture surface cools down, and then I should easily remove the print object. The bed temperature is 30 degrees Celsius. And this temperature tower looks great actually. I reduced the cooling to 30%. But it's dry, there is no stringing at all, and the bridging came out very nice, so definitely it is printable on any temperature between these three. It's time to print the test specimens. All test subjects are printed at 240 degrees Celsius, the bed temperature is 90 degrees. Printing is finished, and now the most fun part. Well, actually it's fun only if you have a flexible plate. So it goes back to this resealable bag with some silica gel inside, but probably later I will move it to some vacuum bag because it will protect better this filament from the moisture. And let's unbox now the PCTG. The spool and the packaging is very similar like the PETG. It's in the vacuum bag, and it is also resealable. There is some silica gel inside the bag and some instructions. And as you can see, it is in some gray or graphite color. So here we can see how many filaments we have in the spool, and there is some kind of scale but without any units on it. Well, anyway, let's start with the temperature tower. I have no experience with this filament at all, but I will set the bed temperature to 100 degrees Celsius, and the temperature tower will start from 270 and go down to 250 degrees Celsius. And I don't want to use any kind of adhesive on this textured PI sheet. Looks okay so far. This is the first layer, bed on 100 degrees Celsius. It's printing the second element on 260 degrees Celsius and looks okay so far. Actually it looks great like the PETG. Printing is finished, and immediately I want to check the bed adhesion. Okay, it is great. Don't forget, now it is on 100 degrees Celsius. And I will wait until it cools down, and then I will remove the temperature tower. The bed is at 40 degrees Celsius. I heard some cracks. Okay. The skirt also came down easily. So there is no problem where it cools down. It came down very easily from the print surface. And basically like the PETG, this also looks great. This is perfect overhang and absolutely no stringing on any temperature, so basically it is printable on any of these three temperature. Don't be confused, this is 270 degrees, but I don't have that type of the element. And test specimens will be printed on 260 degrees Celsius. This is the first layer on 260 degrees Celsius, and it looks okay so far. As you can see, printing is in progress, and the biggest difference from the PETG test specimens is this. Here I will have two test specimens for Izod impact test, just in case if the first one will not break under 0.5 kg hammer. The printing is finished and the bed surface already cooled down. And removing all the skirt. No problems. And immediately after the printing, this filament goes to the resealable bag. And again, let's take a closer look to the temperature towers. Only problem I can see with some stringing, but the overhang and bridging the surfaces came out perfectly with both filaments on any temperature. And then it's time for the mechanical testing. I'm starting with tensile test. So these test objects are printed in horizontal position. Smallest cross-section area is 4 by 4 millimeters, and I'm starting with PETG. And then the PCTG. And all test objects broke on the smaller cross-section area. Next is the layer adhesion test. So these test objects are printed in vertical position. And I'm starting with PETG. And then with PCTG, I noticed quite different in the two measurements. And one of the test objects didn't broke on the smaller cross-section area, but next to the hole. So I decided to reprint and repeat the test with PCTG. And this time I got very similar results, but I will include all 4 in the final results. But they didn't broke on the smaller cross-section area. And the next one is the shear stress. The test object is 5 mm in diameter, but the area is doubled, this shear area. Starting with PETG. This is PCTG. And they all broke on those cross-section area where they should do for the shearing. The next is the bending test, 3-point bending test. I'm starting with PETG. Distance between supports is 50 millimeters. And I want to record the load at 2 millimeter deformation and the maximal load. And this is PCTG. And they all bend quite equally. They didn't broke, just the form. In this torque or twist test, I have these test objects. The diameter is 6 millimeters, and I have this torque meter. This side goes into this torque meter, and the other side goes into the vise. And I will rotate it. I want to record the load at 90-degree angle and the maximal torque. One 1.1. 1.5 was the peak, and I still feel the resistance, and now I feel its break. And now PCTG. .8. 1.2 is the maximum, and I still feel it resist. 1.3. Wow. Okay, now I can feel it, it's weaker. Two twist, I think. Interesting material is the PCTG. Yes, it was weaker, smaller torque on 90-degree angle and the maximal torque, but I could do at least 2 twists before I start feeling that it is weaker material and it will break soon, unlike the PETG. And it's time for temperature test, and according to specifications, I'm expecting that PCTG will perform better in this experiment. And I will follow the temperature with this thermometer, and this is the sensor for it. I want to record the temperature when it reaches approximately 0.5 mm deformation. This is a time lapse of approximately 4 minutes, and I will analyze this frame by frame to get the temperatures of the deformation. As expected, the PCTG was better in this experiment, but I will analyze the footage to see by how many degrees. According to specification, it should be approximately 5 to 6 degrees Celsius. With this Izod impact test, I want to see how brittle is this material, and there were some signs that the PCTG is very tough material. And according to specifications, there is very big chance that the PCTG will not break under this half kilogram hammer, so that's why I have 2 pieces of these test objects. In case if it don't break, then maybe I will lift it higher or maybe switch to 1 kilogram hammer. 0 position. PETG, PCTG, PCTG second time. Well, I don't know the numbers yet, but I'm a little bit disappointed with PCTG because if it would have a strength of 90 kilojoules per square meter, they wouldn't break under half kilogram hammer in this test. And let's analyze the results. So this is the 0 position, and this is the position after breaking PETG, and this is PCTG. And if I left these lines and I measure the distance from the 0 position, I get this distance, but of course I need it in meters to calculate the energy in joules. Or if I divide it by the cross-section area, I can get the kilojoules in square meters. And now I want to measure the hardness with this short durometer, and I will measure perpendicular to the printed layers. But I'm asking for a help again in the comments. Is this important for plastic? Should I do this experiment measurement in the future too? Because with metal I know that a harder metal is more wear resistant, but I'm not sure is this the case with the plastic too. Starting with PETG. 73.5, 72.5. PCTG 70. 70. The next experiment is the creep test. I have these C test specimens, and I will place a constant load on them. This is 1.25 kilogram, and I will measure the distance between these two surfaces, and to be more accurate, I will log the position during the measuring. The creeping is actually the deformation of the material along the time during the constant load. And let's measure the start values. 16.45, 17.61. Day 0, Day 1, Day 2, Day 3, Day 4, Day 5. And it's time for 1 hour heating. The sensor. This is the temperature inside, and this is the alarm temperature, just in case. And now after 1 hour, let's measure the deformations. So this was day 5. Day 5 after 1 hour on 49 degrees Celsius. I already measured everything, and I also want to record the removing of the load. Interesting, during the test the PCTG deformed more, but now when I remove the load and wait 10 minutes, I can see very minimally more permanent deformation on PETG compared to the PCTG. And it's time to analyze the results. This Excel table is downloadable from mytech1.com website. And let's talk about creep test first. So these are those numbers in millimeters which I measured directly, but for the creeping for us, most important is the difference in between these 2 days. And that's what I calculated in this table, and this will be presented in a graph. Maybe one more thing I want to mention here with the numbers, that's this. So this is the layer adhesion test with test specimens printed in vertical position. And first I got very different results, and one of the test specimens didn't even broke on the smaller cross-section area. So I reprinted these test objects in vertical position, and I got these 2 numbers. And basically this is the average value from the 4 test objects. Okay, let's analyze the graphs. So this is the creep test, and as you can see, even after 5 days, not even PETG or PCTG didn't stop with the creeping. And when I placed it into heated oven on 49 degrees Celsius, both had some significant creeping deformation, but of course the PCTG was a little bit better because it has a little bit better thermal resistance. On tensile test, layer adhesion test, in both cases the PETG was better, at least 20% maybe. On shear stress I got very equal results. Usually on bending test and torque test I got very similar results, and in both cases the PETG was better, approximately 15%. Now this is the result of the Izod impact test, and here I was very disappointed with PCTG because according to specifications it should have breaking energy up to 90 kilojoules per square meter, but as you can see this is a little bit more than 4. Yes, it is stronger from PETG, maybe 15 or 20%, but the difference should be at least, I don't know, 10 times stronger. The deformation temperature, here again the PCTG was better, but the difference was maybe 3 or 4 degrees Celsius only. And this is the last measurement, the hardness, which, yes, the PETG was harder in this case, but I'm not really sure should I measure this in future. Is the hardness important with the plastic? And now the conclusions. Well, partly I can confirm that the PCTG has a better thermal resistance and is stronger in impact test, but the difference is very minimal. In all other experiments the PETG is better, and don't forget it is much cheaper. The only reason I can see the reason to use the PCTG is that you really need those few degrees of Celsius of thermal resistance, or maybe those 15% of the impact strength, and you don't want to print inside the enclosure. But if you can print inside the enclosure, definitely I would recommend ABS, and maybe the Fiberlogy could send me their ABS or nylon filaments for similar testing. I will see, because I was curious about the PCTG and PETG, so these I bought myself, but the Fiberlogy mentioned that they are ready to help me, whatever it means. We will see that in the future. Oh yes, I almost forget, I got several requests to test Prusament filaments too. Well, I contacted Prusament several times on different channels, but so far, after, I don't know, 3 weeks, I didn't got even one reply that positive or negative answer. It looks like the Prusament don't communicate with small YouTubers like I am, because you can see their reviews only with the very popular YouTubers. Well, anyway, it looks like I have to use the donations for that, so that's why I'm happy that I have some Patreon or Buy Me a Coffee supporters. Only it takes a little bit time, because some of them are really expensive, those PC Blend or similar. Anyway, I hope you find this video useful. Thank you for watching, and happy printing!